some remarks about the other normal matrix, like anti-Hermitian matrix. A deck is minus A, and obviously because of the minus sign, the eigenvalues of minus A is the negative of the eigenvalue of A. If A has an eigenvalue lambda sub I, then minus A obviously has the eigenvalue minus lambda sub I. But minus A is A dagger. So this is a normal matrix because it's commute with A, obviously. And so this equals to lambda I complex conjugate. So minus lambda I equals to lambda I complex conjugate means that lambda I is purely imaginary. Say, just write like lambda I is purely imaginary, right? And so that's one property of this anti-Hermitian matrix, and it's similar to a Hermitian matrix. Hermitian matrix lambda sub I equals lambda sub I complex conjugate, and that instead of purely imaginary now is purely real. So that Hermitian property of Hermitian operator for anti-Hermitian operator, the lambda I sub I becomes imaginary. For the other cases for unitary matrix. Unitary lambda U dagger equals to U inverse, and U inverse obviously compute with U because the inverse can multiply to the left and right and give you identity matrix. Therefore, it's also normal. So if U has the eigenvalue lambda sub I, then obviously if you multiply by U inverse, then you get U inverse times phi I, and U inverse minus times U is just identity matrix, so altogether is phi I. So U inverse phi I is just lambda I inverse, which is just a number, or you can write it like 1 over lambda sub I times phi I. So, and then, but the U inverse is actually U dagger, and it's normal. So the eigenvalue is lambda I complex conjugate. And by this the equation, you obviously see that the lambda sub I magnitude square, which is lambda I times lambda I complex conjugate, is equals to 1. And or the other way to write this, lambda sub I is e to the I theta I, which is real theta I, a real phase, because this form will make sure that the magnitude square is equals to 1.